Okay, so this is just going to be a recap of convex mirrors doing these ray diagrams. This will help you out with the worksheet that you have in front of you. Convex mirrors are always going to be the same. We draw at least two of the principal rays. There's an example at the top of the sheet that you can take a look at. The first one, if you have a ray that goes straight towards the mirror, it's always going to bounce back so that it traces back to the focal point. The second one is the exact opposite, where it tries to get to the focal point, but it can't because the mirror's in the way, and so therefore it reflects off, but it reflects off straight. Now remember, what the eye sees is going to be your two reflected rays. This ray is going to be reflected, this one right here, and this one right here is going to be reflected. So what your eye sees are these two rays coming at different angles, and if you converge them, then you see that you have a convergence point sitting right here. So your image is going to be situated right there. The third one, if you remember, the third one we talked about is that you can always go straight for the radius of curvature or the center. It's marked as the C on your worksheet, and it'll always go through the same point of convergence. So here's your um, image. Okay, image is always going to be smaller, it's always going to be upright, and it's always going to be virtual for a convex mirror. The size of it is going to be slightly different. The placement between it and the focal point is going to be slightly different depending on where the object is. But in this case, it's always going to end up looking just like this. And these three are always going to be the same: upright, smaller, and virtual. Okay, just reviewing this mirror lens equation: 1 over f is equal to 1 over do plus 1 over di. Is object distance always positive, image distance will always be negative, and focal length will always be negative for this situation. So what I want you to do on that side of the worksheet that has this convex mirror, it's also known as a diverging mirror. What I want you to do is, for every single example, I want you to use each hashtag. So one hash, not hashtag, one hash is going to equal 1 centimeter. I want you to uh, figure out what DO is. I want you to measure DO in terms of the slats on the worksheet. I want you to measure what the focal length is on the worksheet, and I want you to calculate where DI is supposed to be. Okay, once you have calculated where DI is supposed to be, you're going to draw in your ray diagram to show that it is in fact right there. Okay, I want you to do that for every single example. Okay, when you're done with that, you can move on to concave mirrors. Concave mirrors are just as easy as convex, but there's a couple of weird scenarios that get thrown in there. Notice that since the concave mirror is curved this direction, then that puts your radius of curvature and your focal length on the same side of the mirror as your object, and that's going to be important for when we do the calculations. The focal length is going to end up being positive because it's on this side. So the first principal ray that we're going to do is going to be the same thing that we did last time. It's going to go straight at the mirror, and notice that it's bouncing towards the focal point. In this case, it bounces towards the focal point instead of away from the focal point because of how the mirror is bent. If you notice, you can draw out a normal, and that normal traces back to the radius of curvature like we talked about in class. The second one is going to be very similar again to the second one that we had for the other situation. It's going to have a principal ray that goes to the focal point, and you notice that it bounces back straight. You already have a point of convergence right here. You already know where the image is going to be. You can throw in the last one, which is the same as the last one for convex, which goes through the radius of curvature and bounces back straight along that path. Okay, here is your image. The image looks a little bit different than what it did for convex, right? It looks a little bit different. It is upside down, or something that we call inverted. And notice what's making up this image. This image is made up of actual light rays. It is made up of actual light rays. These are not reflected light rays that are on the other side of the mirror. These are made up of actual light rays. Okay, so this is actually a real image. So it is a real image. It is still smaller. It is a real image. It's smaller, but it is inverted. And you'll see later on that every time you have a real image, that real image is inverted. These two go hand in hand, real and inverted. Okay. Now there's some scenarios that we can go through. What happens if sorry, 1 second. Notice that the image happens to be on the same side as the object. The focal length happens to be on the same side as the object. So we say that object distance is always positive, therefore the other two are going to be positive as well. Okay, so for this equation, do the same thing that you did for convex on concave. I want you to take a look and measure where DO is, measure where the focal length is, calculate where DI is supposed to be, and then draw on your ray diagram for that. Okay. What happens if the object happens to be right on top of the focal point? We couldn't do this with a convex mirror. We couldn't do this with a convex mirror because the focal point was on the other side. So let's try to do our principal rays. The first one we can still do. It goes straight at it and bounces back normally through the focal point. But look at the second one. The second one goes through the focal point and bounces back straight. We actually can't do that one because you're sitting right on top of the focal point. It cannot happen. The third one you could do going through the radius of curvature, except it's originating here, so it's a little bit different. So it goes through the radius of curvature, and that's actually a bad drawing. I'm going to erase that and just let mine do what it's supposed to do. You could do a separate third one, which is making use of the law of reflection by doing something like this, where you go towards the axis and it bounces back along that same angle. What do you notice about these two light rays? They're exactly parallel to each other. Okay, this is showing you that if you are sitting on top of the focal point, you create no image. Okay, no image. Every ray that you were to could draw will always end up being perpendicular to, or excuse me, parallel to all the other rays. Okay, again, if it comes through the radius of curvature, okay, and if I drew that better, it would look like it was parallel. So if you're sitting on top of the focal point, you create no image whatsoever. Okay, what happens if you're inside the focal point? If you're inside the focal point, we're going to still try to do the same principal rays that we have in the past. And so this is going to be going to the to the mirror and bouncing back to the focal point. That's still fine. Okay. We can go from the focal point bouncing back straight. Okay. Just realize that if it's originating from the arrow, this line is not actually there. I'm just showing you as going through the focal point. So it's originating from the arrow and bouncing back straight. Now, take a look at the reflections again. We care about reflections. This one's a reflection, and this one's a reflection. Are these two light rays parallel? You should be able to say that they're not. So if we take a look at how that reflection converges, it converges over here. Here's our point of convergence. You could do the third one from the radius of curvature, and you'd see that the reflection still shows that point of convergence over here. Take a look at your image. Okay, this is the first time that we've encountered an image that is bigger. Okay, this is an enlarged image. Is the image real or virtual? Well, it's on the opposite side of the mirror as the object, so therefore it is a virtual image. So in this case, we're going to say it's upright, it's virtual. Again, those two go hand in hand. Upright and virtual always go hand in hand if inverted and real do. And this one is actually enlarged. It's bigger. It is bigger than the object. So if we take a look at our lens equation, again, same equation. Object distance, always positive. Focal length for these types of mirrors, always positive because it's on the same side as the object. But our image distance now all of a sudden becomes negative. Okay, this works mathematically if you actually do stick in the numbers. This works because the focal length is always bigger than the object distance. So when that happens, you end up getting a negative image distance. So same thing that we've done before is I want you to, on your sheet, I want you to measure DO, I want you to measure F, and calculate DI and show your equation or show your ray diagram to support it. Okay, that's it.